In this paper, we present a novel pneumatic augmentation to legged robots for the purpose of energy accumulation and power amplification. We implement the proposed framework on a one-legged hopping robot, and we show that with the appended pneumatic system, the robot is able to harvest and store energy continuously from periodic hopping motion, and then releases stored energy as needed to perform highly explosive tasks such as jumping over large obstacles. As legged robots often perform cyclic motions to realize locomotion behaviors, negative work has to be done to the robot during each cycle. Taking hopping as an example, before accelerating upwards to lift off the ground, the robots must decelerate to a complete stop in a vertical direction in the descending phase by performing negative work on itself. We thus aim to convert the negative work to utilizable energy that can be stored continuously and then used by the robot later to increase its power output. We start by building a planar hopping robot that is originally actuated by electric motors. The proposed pneumatic augmentation is then designed and installed on the robot. The pneumatic system is composed of a pump, a tank, and a pneumatic actuator. The pump and the pneumatic actuator are installed in parallel between the thigh and the shin and act as pneumatic joints, the forces of which are carefully identified via a tensile tester. During periodic hopping, the pump performs the negative work to the robot and stores the energy in the tank in the form of air pressure. The pressure stored in the tank thus increases over consecutive hopping cycles. Once the pressure in the tank reaches a certain value, the robot releases the air pressure to actuate the pneumatic actuator, giving it a surge of power output to complete explosive tasks. For all hopping behaviors, the trajectories are optimized via direct collocation and stabilized by task space position and force controllers. Without the pneumatic augmentation, the electric motors alone can also realize a maximum apex height of around 4.3 centimeters on average. With the pneumatic augmentation, the robot can increase its hopping height to an average of 23.4 centimeters. This is equivalent to a power amplification per cycle of around 5.4 times. The power amplification can be useful for the robot to perform explosive behaviors such as jumping over large obstacles. Here we demonstrate the scenarios that without using the pneumatic augmentation, the robot fails to move over the obstacle, while with the pneumatic augmentation, the robot can store the energy first and then release it to jump over the obstacle successfully. The stored energy in the tank is proportional to the air pressure. Thus, the explosive power output is directly related to the increase in the release air pressure. The tank has remaining air pressure after one explosive hop, which can be used to perform a consecutive enhanced hop. More importantly, the weight of the robot plays an important role in the power amplification. The increase of the robot's weight decreases the regular jump height, but it can increase the maximum air pressure the pump can achieve, which directly affects the maximum stored energy in its power output. This thus provides a guideline for future design optimizations for pneumatic augmentation. In conclusion, we successfully demonstrated that the proposed framework enables traditional legged robots to convert negative work to storable air pressure and then perform high power output behaviors. The result from the hopping robot indicates a promising design and control paradigm for power amplifications on a highly dynamic legged robot.